Okay, so at the end of last time we were talking about the sequence criterion for closedness. Now, remember, we have a definition of closed, meaning that the complement should be open, but sometimes it's useful to be able to check things in terms of sequences. And in terms of sequences, you can tell if a set is closed by finding out whether or not you can escape from the set using taking the limit of a sequence. So if you take a sequence in the set, is it possible that the limit of that sequence, if it exists, might be outside the set? Well, for a closed set, that can't happen, but for any other kind of set, it can. And that's the sequence criterion for closedness. Now, that may sound a bit strange if you haven't seen this phenomenon before, so let me have a look at an example of a set and a sequence escaping from it. So here's a nice example of a sequence and a set, or a set and a sequence. So let's consider the set E to be, we'll take the open interval -1, 1 contained in the real line. And we'll take the sequence xn equals 1 over 2n. I take 1 over n, except that the first term wouldn't be in the set. So I'll take 1 over 2n just to be safe. Remember, our natural numbers start at 1, so that you're not divided by 0 here. Then that sequence is in E. Oh, it's a bad example. I see what I've done wrong. Yes, sorry. Let me just correct that. I'll start from 0. Otherwise, it's not a good example. So we'll start again. We'll start with the open interval 0, 1 contained in R, and a sequence xn equals 1 over 2n. Then it's still a sequence in E. But in R, the limit as n tends to infinity of xn is 0, which is not in E. It would have been if I'd gone from -1 up to 1, so that's why that would have been a bad example. So here's an example of a sequence of elements of E whose limit is not in E. The sequence criterion for closedness confirms a fact we already knew already, that means this set E is not closed. We already knew that. That E is not closed. So this will give you an alternative way of checking that a set is not closed if you can find a sequence in the set which has got a limit that's outside the set. And that is another valid way of showing things are not closed once we've proven the sequence criterion for closedness, which is the final result of chapter 5. So let's have another look at that. And then I think about some of the logic of the situation. You can do some of this by contradiction. I'm going to try and do it all by direct proof using contrapositives without contradiction today. But I did a proof by contradiction last year, so it gives you an alternative proof structure. So let's have a look at this. That's one that says that C is closed. That's the same as saying that C complement equals R to the D minus C is open. let's have a look at the contrapositives, or rather, let's have a look at the negations. We're going to prove not 1 if and only if not 2, but we're going to have to work out what they say. So we're going to prove both contrapositives. But that means we have to work out what the negations really are. Well, not 1 says C is not closed. So if C is not closed, does that mean that C is open, or does it mean something else? What does it mean to say that C is not closed? What's the correct negation of C is not closed in terms of open sets? Anybody? C is closed if and only if C complement is open. So C is not closed if and only if C complement is not open. That's right. C complement is open. And C is not closed if and only if C complement is not open. And that's what we're going to be using in a minute. It's also worth looking at the negation of 2. The negation of for every sequence something happens is that there exists at least one sequence in C where the opposite happens. So not 2 says that there is a sequence in C which converges in R to the D with a limit outside C. So there is such. So for every sequence which converges in R to the D, that's the quantified bit. So that turns into there exists a sequence in T which converges in R to the D, and then the statement becomes false, which is the limit could be outside C. So not 2 says there exists a sequence xn contained in C which converges in R to the D to some, that should be vectors, some x in C complement. So these are the negations we're going to prove equivalent. So we'll start with not 1 implies not 2. And we'll start with not 1 implies not 2, as I say. So given that C is not closed, we have that C complement is not open. And so, in terms of nint, that means the nint to C complement is not empty. there is at least one non-interior point in C complement. So let's say X is in nid to C complement. And now we're going to prove not 2 by proving that there's a sequence in C which converges to X. And that will prove not 2 if you look at what we said above. We prove that there is a sequence in C converging to X, which, by our above comments, proves that 2 is false. Okay, so now this is the tricky bit. This is one of those bits where you have to have an idea. Let's have a little picture of where X is. So here's C, and here's C complement, and here is X. And in spite of what it looks like, X is actually not in C. X is in nid a C complement. This is one of those optional diagrams, by the way. X is in nid to C complement. These diagrams don't prove anything, but they do help you see why the proof works. So notice that X is not in C. X is in C complement. It's somewhere not in C but at the edge of C, and we're going to try to prove that there's some sequence in C converging to X. Now all we know is that X is not an interior point to C complement, and to not be an interior point, to be an interior point in C complement means, of course, you're in C complement and you're not in the interior, means that for every little positive radius ball you take, no matter how small a ball you take round X, so let's call that BR of X, every little ball centred on X has a point of C in it. So since X is in the interior, a C complement, we now go back to the formal proof. We get the following statement. For all positive real numbers R, no matter how small, there exists a Y in C intercepted BR of X. Now, why is that? Well, why do I say it's in C? Well, it's because it's in C complement complement. So C complement complement is C. So the point in that ball that isn't in C complement, to not be in C complement means you must be in C. And let's call that equation star. And there's my little, a little comment there, note, Y not in C complement implies that Y is in C. So that's your point Y in the ball that's not in C complement, and that forces it to be in C. Now, That's equation star, and what we have to do is use star to get a sequence. But star says something about all positive real numbers are. To get a sequence out of it, we want something for each natural number. So this is one of those ideas. It's an idea that comes up several times in this module, and it's one of the few ideas that's not obvious, and so it's one of those ideas you actually do need to know. And the idea is that we only use the real numbers r equals 1 over n for natural numbers n, or any other sequence which tends to 0. So we apply star with r equals 1, a half, a third, and so on. And each time you get another point, and each time you get one of these points, that gives you another term in a sequence. So for each natural number n, we can find an xn, this is the y, but I'll call it xn, in C, with xn in B 1 over n of x, and actually that's it. That's what star tells you. And now, having done that, having thrown away some of the information, apparently, because we only used some of the values of little r that were available, it turns out we finished. But then, norm of xn minus, well, naught is less root of norm of xn minus x is less than or equal to, it's actually less than 1 over n for natural numbers n, and so norm xn minus x tends to 0. It's a sandwich theorem, really. You don't really have to say that. Norm xn minus x tends to 0. And then tends to infinity, i.e. xn tends to x, and then tends to infinity. So what's that? It's a sequence in C converging to x. X is in C complement, so this shows that 2 is false. As claimed. And we've done half of the proof. Any questions about that half of the proof? So we showed if you're not closed, then there is at least one sequence in the set that converges in R to the D to some point that's outside the set. Now we need the converse, which again, this time we use not 2 implies not 1. So, given that given that 2 is false, then there exists a sequence xn contained in C which converges in R to the D and whose limit is outside C. So to some point x in C complement. So it's a similar diagram to before, only we're trying to go the other way. So what we'll do is we'll prove that X is in the interior C complement. So it's actually the same diagram as before. So I won't bother redrawing it. Look at the diagram we had before, and we'll prove that X is in the interior of C complement, so that C complement is not open and C is not closed as required. Of course, we have to prove this. Now, I often do this bit by contradiction because I feel it's sort of a proof by contradiction, but you can just about do it directly. And that's what I'm going to do now. So again, almost the same picture as last time. If you look back at the sketch we did before, to save me from drawing it again, we let R greater than 0, and we'll show that, of course, X is in C complement, so I'll just remind you, X is in C complement, so to prove it's in the interior, we just have to prove it's not an interior point, which means that for every R greater than 0, we've got to show that that ball is not contained in C complement. To do that, we have to prove that there's at least one point of C in there. We show that BR of X intersected with the complement of C complement, which is C, is not empty. So, and now we sort of know how to do it. Because, okay, it's about time I redrew the diagram, I think. But this time there's a sequence involved. So here we go, the usual optional diagram. Here's C. It's essentially the same diagram as before. Here's C complement. Here's X. Here's the ball that we're considering, and we want to find there's at least one point of C in it. At least one point outside C complement has to be in here. So here's BR of X. But to help us, we've got a sequence in C that's converging to X. Oh, again, as before, X is in C complement, and X is in fact, into C complement. And to help us, we've got a sequence in C that converges to X. Now, some of those xn's may be outside, some of them will be inside that ball, and that's what we're going to use. We've got to find a point of C in that ball. We're going to use one of the xn's. Since xn tends to x as n tends to infinity, there exists some capital number n in the natural numbers such that for all n greater than capital N, we have xn is in BR of X. And then in particular, X capital N is in C intersected BR of X. So that shows that set's not empty. So what do we do? Thus, X is in the interior C complement as required. And the proof is finished. Okay. Any questions on that proof or on anything from chapter 5 before we move on to chapter 6? If not, then I'll pause the recording and give you a little break before we start chapter 6.